Okay, so this is the third lecture of the group theory course. The first two lectures that we did last week or the week before that, just a brief summary of them. The first lecture we discussed chapter 1 of the textbook. This is our textbook, and basically we discussed some basic definitions of group, cosets, classes. We discussed the relationship between classes and symmetry, different types of symmetry operations of the group. The same type of symmetry operation will belong to the same class, roughly. That's the idea. We discussed factor groups, and we had one problem, which is problem 1.3 of the textbook. In the second lecture, we discussed chapter 2, and then we introduced the concept of representations. Those are matrices that satisfy the same multiplication table of the group. We introduced the concept of reducible and irreducible representations. And finally, we discussed one of the most important theorems of group theory, which is the wonderful Orthogonality Theorem. And we had two problems in the second problem set, problem 1.4, problem 2.2. So if you are starting to follow this course now, basically these are the things that you need to review so that you are in the same foot as other people that have followed the course from the start. Okay, so this is now we start the third lecture. This is also corresponding to the chapter 3 of our textbook, in which we're going to discuss what the character of a group representation. Chapter 3 will consist of two lectures today and next lecture that it's going to be next Wednesday. Okay, so first of all, why we need to, or we want to introduce the concept of character. Character are simply the trace of the representation. So what happens is it's much simpler and is sufficient in most cases of group theory to work not with the representation, the complete representation, matrix representation of the group, but it is sufficient to work with the character. And also this is a good idea to do that, because characters are invariant under a similarity transformation. For instance, if you take as we discussed last lecture, if you have a matrix, let's see, if you have a matrix D gamma J of R, and the notation here is that this is a matrix representation, D corresponding to the representation gamma J, and for a given symmetry operation or member of the group R. So if this is a representation of the group for all matrix for all symmetry operations R, then so if this is a representation, then if you do a similarity transformation, like this, and I could call it I don't know, D prime. This is also a representation. Okay, So you have this multiplicity of representation or ambiguity, if you want. But this ambiguity doesn't happen. It doesn't occur with characters, because characters are invariant under similarity transformation, like that. So this is one of the reasons to work with characters, and of course the other reason is that it's much simpler to work with a number, which is the trace of a matrix, than working with the matrix itself. Okay, so the character is invariant. So again, as I have said already, what is the character? The character is simply the trace of a matrix. So if you take a given matrix representation D corresponding to the representation gamma J of a given symmetry operation R, the character corresponding, we use the letter chi for character. The character for that representation is simply the trace of this matrix, which is the sum of all diagonal elements. Okay. All right. So so there is a very important result relating characters and classes, and which is this, is a theorem which says that the character for each element in a class is the same. So this is very so all the group elements that belong to the same class, they have the same character. Their matrix will have the same trace. So and this is very easy to show, because if you remember, what defines the condition that two group elements are in the same class is this, again, this similarity transformation. So if this is true for a certain group element Y, then that means that A and B are in the same class. Okay, we have seen this last time. So it is immediate then that since the trace is invariant under this similarity transformation, also because of the fact that all group elements can be represented by unitary matrices, then you have that the trace of A is equal to the trace of B, right? The trace of A is equal to the trace of B, and then A and B have the same character. So the character of A is equal to the character of B if they belong to the same class. Okay, so this is a simple result to show. So this is a very, again, as I said, very useful and important result regarding characters, and one of the reasons why characters are so useful is that this correspondence. So if you have the same type of symmetry operation, then the group element will belong, two group elements that have this correspond to the same type of symmetry operation, they will belong to the same class, and then they will have the same character. This has very important result was called by von Vleck as the great beauty of character, and this allows us to introduce this very important concept in group theory, which is the character table. So the character table, it's a way to display all the characters of a given group for each class. So you separate in each row of the table, you have the different classes, and in each line, in each column you have different classes, and in each row you have the different irreducible representations of the group. So I'm giving you this example based on the group P3, that is the permutation group of three objects that we discussed last time. And I can already tell you that this group, well, we have discussed that. We have discussed that the group P3 is equivalent to the group of symmetry operations of equilateral triangle, right? So, and this is, I'm going to introduce this notation in the next lecture. This is what we call the group D3, the point group D3. So just wait until next lecture that we're going to discuss this notation. So, so this is then the character table for group D3. So as I said, all the group elements belonging to the same class, they correspond to one column of the table. If you remember our discussion last time, you will see that for this group we had three different classes. One is the identity. The identity is always in a class by itself. Then we had the 3C2. 3C2 means that we had three symmetry axes that had the twofold rotation symmetry. These are the three. Let me draw it again. If you remember, we had our triangle, and we had these three different symmetry axes of the triangle that if you rotate about those axes by pi, then these corresponds to symmetry operations of the group. So these are these three symmetry operations A, B, C, and then they belong to the same class. And then you also have a class C3. Class C3, we have two members, D and F, and they correspond to rotations of 2 pi over 3 and minus 2 pi over 3 over this perpendicular axis. Okay, so we have discussed this last time. So this is a typical notation that we use to symbolize a class by indicating what symmetry operations it corresponds to, and this number 3 and 2 indicates the number of group elements in the class. 3 elements, 2 elements. And in the different rows you have the different irreducible representations. As we have discussed last time, for this group we have 3 irreducible representations. Gamma 1, which is just the identity representations of the number 1 for all elements. Gamma 1 prime, we have either plus 1 or minus 1, is also a one-dimensional representation. And gamma 2, which is a two-dimensional representation corresponding to these 2 by 2 matrices. Okay, and these are the characters. You can verify that, for instance, I don't know, the trace of B is 0, so that's why the character corresponding to this class is 0, and you can basically verify that this table is correct for all group elements. Okay, so these is one example of a character table. As I said, it's going to be a very central object in this course. Alright, so now we come to the wonderful orthogonality theorem for character. So it's very similar, but much simpler than the wonderful orthogonality theorem for representations. And it basically is. This is one way to write it. So this is the sum over all group elements R. This is gamma j and gamma j prime are two different representations, either different or equal representations. And if you do this sum of characters for chi of r and chi of r minus 1, the inverse of r, then the sum is either 0 if gamma j is not equal to gamma j prime, if you have two different representations, and if you have the same representation, then this sum is equal to h, where h is the order of the group. Okay, you can write the same result this way by using the fact that representations are unitary. So you can write the chi of r minus 1 as the complex of chi of r. So this is a more common way to write this wonderful orthogonality theorem for classes. Okay, all right. So first of all, let us just initially verify this theorem using again the group P3 as an example. So this is the character table again of group P3, and we can, for instance, I don't know, we can just verify this for, let's take for instance gamma, sorry, let's take gamma gamma 1 and gamma 1 prime. So if I take gamma 1 and gamma 1 prime, so these are two different representations, so the result of this sum should be 0. Okay, so let's just verify. So basically what we need to do is to sum over all group elements the product of the characters of gamma 1 and gamma 1 prime. So let's do it. So the first we have the C1 class, the identity class. So it's just 1 times 1. Then summing over all the elements of the C2 class. Then you have a factor of 3 because you have 3 elements in this class, and you have the product of 1. So you have 1 times minus 1, right? So we have 1. So it's just this, times this, which is the number of elements in this class. And then plus 2 times 1 times 1. So this is 1 minus 3 plus 2, which is equal to 0. So that is verified. So let's see. Well, let's take now gamma 2 and gamma 2 as gamma j and gamma j prime. If you do that, the result, since we are dealing with the same representation, the result should be equal to h, which is the order of the group, and it should be 6, right? It should be 6. So let's see. So this is, if you take this, multiply by itself, 2 plus 2, which is 4, plus 0, plus 1, minus 1 times minus 1, which is 2. Times 2. This is 1 times 2, which is the number of elements here, right? So this is 6. Okay, so we are just verifying this wonderful orthogonality theorem for character using this simple example. But we can also, it's a very simple proof to show to you. So let's do this proof. It's in the textbook, but just let's do this one so that we can appreciate that. So the way to prove this is that we start with the wonderful orthogonality theorem for representations that we discussed last time. So it's the sum over all group elements, and then you have the matrix representations corresponding to gamma j of R, and the mu prime gamma j prime of R minus 1, and this should be H over Lj, the dimensionality of representation Lj, and they have three deltas here: delta of gamma j prime, delta of mu prime, delta of mu prime. Okay, this is the wonderful orthogonality theorem that we have seen last time. So what we do is you simply take the diagonal elements, right? Let's just take the diagonal elements of this general result. So instead of mu nu, you use mu. So you have a sum over R d mu nu gamma j of R d in this case I will write mu prime gamma j prime R minus 1, and this should be equal to H over Lj delta gamma j it should be gamma j prime, and this should be basically delta mu prime, and this is also delta mu prime, okay, because I took nu to be equal to mu, and nu prime to be equal to mu prime. Okay, so now I have the diagonal element, so I can take the trace. Let me just take the trace by summing over mu, right? And I will leave this summation over R here, and I will sum over mu. And we'll sum over mu prime. So I'm just taking the trace of the two matrices. And then I'm summing here over mu prime, I should sum over mu prime also here in the right hand side, okay? So this is then H over Lj gamma delta gamma j prime, and then I have to sum over mu and mu prime here in the right hand side too, and I'm basically summing two delta functions here. Okay, all right. So this summation it's very easy to do, right? Because basically I'm summing just delta functions, and these will give me just the dimensionality of the representation. I'm summing the diagonal elements of it's like I'm finding the trace of a diagonal matrix, right? So this is Lj, which is the dimensionality of the representation. So if it's a one-dimensional representation is 1, if it's a 2x2 identity is 2, so on and so forth. And this will cancel with this one. Okay, and of course these are simply the characters, right? These are the traces, so they are what we call characters. So this is the character of corresponding to the representation gamma j and symmetry operation R, and this is the character of the representation gamma j prime, symmetry operation R minus 1, R inverse. Okay. So then the final result is a sum over R. Oops. So this is the final result, sum over R of the products of characters of two representations, gamma j and gamma j prime, corresponding to this group elements R and inverse of R, is simply 0 if I am dealing with the same with different representations, or it is equal to H if I'm dealing with the same representation. So this is the wonderful orthogonality theorem for characters. Okay. All right. So let me just, I used too much space here. Basically, there is an equivalent. So let me erase this just for a minute so that we can read this. An equivalent way to write the same theorem is this one. Instead of summing over all group elements R, I sum over all classes. So sum over K is a sum of classes, and I'm using the fact that the characters are the same if we have group elements belonging to the same class. So I can simply, instead of writing the wonderful orthogonality theorem for characters in the usual way, I can write in the simpler way. Instead of summing over characters, I sum over classes, and this is a sum over class. And this is the number of elements in each class. Number of elements, group elements in each class. And then I get the same result. Okay? Alright. So this is basically what I did in this example. You see, I multiplied by the number of elements in a class whenever that was appropriate to get the final result. Okay, so this is a very important theorem, as I said. Characters will tell us if a given representation is reducible, because otherwise it will not satisfy this theorem. This theorem is valid only for irreducible representations. It will tell us if we have found all the representations in a group. We're gonna see actually this we're gonna see more clearly next lecture. And it will tell us if two representations are equivalent. If two representations are equivalent, they will have the same characters. So this is I'm not showing this result. This is just information for you. Okay. All right. So let us discuss a little bit the importance of characters in reducible representations, and how we can decompose reducible representations into irreducible representations. And this is very important in group theory. So this is an important result. If I have a reducible representation, I can write the character of a reducible representation as a linear combination of the characters of all irreducible representations gamma I in the group. So these are the characters of the irreducible representations, and these are coefficients AI that are unique. This means that there is a unique way to decompose a reducible representation into irreducible ones. And it's easy to see this as an example. I'm going to show you in a more formal way, but before that, let us just see that as an example using the reducible representation that we discussed last time for the group P3. As we discussed, we have three irreducible representations: gamma 1, gamma 1 prime, gamma 2, right? And I could arbitrarily construct a reducible representation that I call gamma R simply by making blocks. For each matrix, I could make blocks of the three irreducible representations in this way. And there's a notation to represent this, which is this: the reducible representation as a sum of three reducible representations. So you can see immediately then that this sum should correspond to the sum of characters, right? Because, well, simply if you combine the three matrices in block form, it's obvious that the character of the large matrices are going to be basically the sum of characters of the smaller matrices. Okay. So this is an example of how this thing works, but it's not. I mean, AI. This is an arbitrary combination, right? AI. It doesn't have to be equal to 1 for all cases. I choose a specific example in which AI is equal to 1. Okay, 1, 1, 1. But it could be a different linear combination. Okay, so let's see in general the proof of this theorem. So sorry. Let's prove this theorem. So I basically oops. Okay, basically this is the result I want to show, that the character so since the characters of all classes are the same, I can, instead of working with a character for a given group element, I can work with the character of a class. Okay, so this is the character for the reducible representation of a given class CK, and I want to show that this can be written as a unique linear combination of the characters linear combination with coefficients ai of the characters of irreducible representations gamma I of ck. Okay, so I'm going to show this result just by explicitly calculating these coefficients ai. Okay, so I start this by considering the following quantity that I call S of j. S of j is the sum over classes, and nk is the number of elements in each class, and have here the characters for each irreducible representation, complex conjugated, and here we have the characters for the reducible representation. Okay, let me call that quantity Sj. All right. Okay, so now I use the fact that I use this fact that I can express. This is an assumption, okay? I will use this assumption that I can express this quantity as this linear combination. So let me just substitute it there. So Sj is going to be equal to sum over k and k chi of gamma j ck. And then I will write this as a sum of over all irreducible representations of ai chi gamma I ck of ck. Okay. All right. So I will just switch the order of the two summations here. So this is then equal to sum over irreducible representations gamma I, ai, and then what I have here is the sum over classes, k, number of elements in each class, and chi gamma j ck. Let's conjugate, and chi gamma I ck. Okay. All right. So then we apply the wonderful orthogonality theorem, okay, for characters. We can see that this is exactly what we have in the wonderful orthogonality theorem. So this is equal to h, the order of the group, delta of gamma I, gamma j. Okay. So this is in the end. This is equal to a sum over gamma I, ai, h, delta, gamma I, gamma j. Okay? All right. So, so this is simply, well, this is simply equal to. This is only different from 0 when gamma I equals to gamma j. So applying this delta condition here, this is simply a j h. Okay. So we have related this quantity that we apparently arbitrarily wrote as this quantity. We have related it to aj. So basically, using this result, we can explicitly have an expression for this coefficients aj are equal to Sj over h, which is 1 over h, this quantity right here, right? So basically this is equal to a sum over k, and k character. All right. So what we have done here is we have written an expression for aj. So given a reducible representation with characters chi of ck, I can basically write this expression and define the coefficients aj that allow me to essentially decompose the character of a reducible representation into a sum of characters of irreducible representations multiplied by these coefficients. So I have shown this by explicitly calculating these coefficients. So let me discuss a little bit about the importance of this result. It may be not so apparent now, but what we are going to see in the next few lectures is this is a very interesting and important result that will appear in many cases, in many situations in group theory, specifically when you have a higher symmetry. Let's say if you have a crystal with cubic symmetry, and for some reason you break this cubic symmetry into a lower symmetry by, for instance, applying strain or I don't know, if you have a defect in the lattice that reduces the symmetry. So what we are going to see is that the irreducible representations of the more symmetric group, in this case of a cubic group, when you reduce the symmetry, these representations will correspond to reducible representations of the lower symmetry groups. And if you now decompose this reducible representation into the irreducible representations of the lower symmetry group, then you will find a way to, for instance, understand how different types of degenerate levels in a Hamiltonian, how they will split and decompose into lower degeneracy group. For instance, if you have a fivefold degenerate state corresponding to a fivefold representation of dimensionality 5, if this breaks into 3 plus 2 dimensionalities in the lower symmetry group, then the result is that if you have a fivefold degenerate level in a cubic system, this will break into a twofold and a threefold degenerate state in the lower symmetry situation when you break the symmetry. Okay, this may be not so clear now, but this will become more clear in the future, and I'm just anticipating this result because this decomposition here that we have discussed is a very important result in group theory. Okay. All right. So let me now discuss the Another very important result regarding characters, which is that characters allow us to obtain the number of irreducible representations in a group and actually relate that to the number of classes. So this is a very important result. The number of irreducible representations in a group is equal to the number of classes. So that means that, let me come back to the character table that I have shown you before. This, you can see this as an example here. You can see that we have 3 classes in the P3 group, and also we have 3 different irreducible representations. So this is a general result. So for every group, the number of classes is equal to the number of irreducible representations. So this is not at all an obvious result. So, therefore, it's a very important result that let us try to show it. So the number of classes, if you remember, it's the number of different types of symmetry operations in your system. So, and then you can, for a given system, you can basically try to figure out what are the different types of symmetry operations that you have, and this will give you the number of classes, and also by this theorem it will give you precisely the same number of irreducible representations. Okay? All right. So let me show this result. It's actually very simple. Again, this is the wonderful orthogonality theorem for character. So this is the sum of all classes, the number of elements in each class, and the characters for class, different classes and different irreducible representations. And I can write this equation in a more symmetric way, simply by taking, well, this h, the order of the group goes into the denominator here, and then I split this in the product of 2 parts using the square root. So I have identical, not identical, but very similar factors in this product. So this is a normalized and more symmetric way to write this result. Okay. So let's see. Let me just rewrite the character table of the P3 group by normalizing the characters using these factors. Okay. If I do that, this is the result I get. For instance, this row becomes this row, the second row becomes the second row here, and so on and so forth. What I basically did was just to normalize by nk over h. Nk, the number of elements in each class, h, the order of the group. So here, instead of 1, I have square root of 1 over 6. And I basically do the same for all group elements. Okay. So what is interesting here is that when I do this, the character table can be written as a matrix, a 3 by 3 matrix, like this one. This is a 3 by 3 matrix. And each row of this matrix, you can think of a vector. You have 3 rows, and then we have 3 vectors, v1, v2, and v3. And what this equation means is essentially an orthogonality relation, or better, an orthonormality relation between these 3 vectors. Okay? This basically means that v1 is orthogonal to v2, v1 is orthogonal to v3, v2 is orthogonal to v3, and they are normalized. The norm of each vector is 1. Okay, this is what this equation means. Okay, so now these are vectors in a three-dimensional space, okay, because we have three classes. The number of columns is 3. But then it is a very simple result of linear algebra. You can only have, in a space of dimensionality 3, you can only have 3 vectors that are orthogonal to each other and nonlinear dependent to each other. Okay, the number of 3 vectors that you can have in a space of dimension 3 that are orthogonal to each other is 3. So it's a very simple result of linear algebra that you can, if you have a space of dimensionality 3 and then the number of columns is 3, then the number of rows must be also 3. So, and the number of rows is related, as I said, to the number of irreducible representations. So this is a very simple way to show that the number of irreducible representations is equal to the number of classes for any group. Okay? And this is a very important result too. All right. So, okay. So I have shown you then that the wonderful orthogonality theorem for characters then can be seen or can be interpreted as orthogonality between rows, orthogonality between representations, okay? Orthogonality between representations. So there is a second orthogonality relation for characters that actually corresponds to an orthogonality relation between classes. Orthogonality relation between classes, which is basically in this table an orthogonality not between rows, different rows, but now orthogonality between different columns, right? And this is also very easy and simple to see. Using this example, you can see that every column is also orthogonal to each other. Okay? And this is basically what the second orthogonality relation for character means. So instead of summing over all classes, now you sum over all irreducible representations. And these are the characters corresponding to different classes ck and ck prime for the same representation gamma j, and the result is this is equal to 0 unless I have the same class. Ck is equal to ck prime, k is equal to k prime. So and if this is the case, then this is equal to h, the number of elements in the group. Okay. So the proof for this theorem is very similar to the one we did before. So I'm not gonna do it here. Just leave you that as an example, or I will leave you as a homework for you. But let me just work out some examples here. Let's see. Let's use this relation. Let's use this relation to verify this theorem for the group P3 using this character table. Okay. For instance, let's do the orthogonality between the class C1 and the class C2. Okay, so that means I have to sum over all representations. So let's see. This is 1 times 1, the first row. The second row is 1 times minus 1. and the third row is 2 times 0, and this is equal to 0. So I have just shown you that this theorem works for these two these two columns. Let me do now. Let's show the normalization for the third class, the class C3. So let's take these numbers now and use this relation and see that the result is going to be equal to h. Okay, so this is 1 times 1 plus 1 times 1 plus minus 1 times minus 1, and this is multiplied by nk. By nk is the number of elements in each class, which in this case is 2. Okay, so it's 1 plus 1 plus 1, 3 times 2. This is equal to 6, which is the order of the group. So we have just verified this result, and as I said, the complete proof I can leave it as a homework to you. It's in the textbook. Okay. So let me now introduce to you and define a special type of reducible representation, which is the so-called regular representation of the group. The regular representation, it is constructed in the following way. You take a group, you take the multiplication table of the group, and you rearrange the rows and columns so that the identity element E is always in the diagonal. Okay, so let me do it by example using the P3 group. So I just did that for the P3 group. I rearranged the order of the different elements so that I have the identity always in the diagonal of the multiplication table. To do that, what I need to do is basically, if this is an element A, the second column is the element A, then the second row must be the inverse of A, which is in this case is also A. But you do this for all elements of the group. The third column is B, so the third row is the inverse of B, which is B. And the same for C, the same for D. In the case of D, is the fifth column D, then the fifth row is the inverse of D, which is F in our case. Okay, so you rearrange all the columns and rows in a way. This is not a unique way to do it, but this is one of the possible ways to do it. But you rearrange such that the identity element is always in the diagonal. Okay, after you do that, you use this table, this multiplication table, to construct a matrix, a 6 by 6 matrix. You have 6 elements in the group, so you construct a 6 by 6 square matrix. So the dimensionality of the regular representation is going to be equal to the order of the group. So for each group element X, you construct a 6 by 6 matrix just by putting a number 1 wherever the element X appears, and the number 0 otherwise. For instance, for the identity operation, the matrix corresponding to the regular representation is basically the diagonal matrix, okay? Because you just put ones whenever the identity appears here in this table. Let's see the case of the matrix corresponding to the operation A, the symmetry operation A. You see whenever A appears in this table, you put ones, and then you construct this matrix. Okay. And then you do this for all elements of the group, and then you're going to have a set of 6 matrices. And first I'm going to show you that this is a representation of the group. Okay? And this is actually what is called the so-called regular representation of the group. You can see already that the only matrix with non-zero character is the identity. Okay? So the only group element or matrix of corresponding to a group element which has non-zero character is the identity. So the character is going to be 6, the order of the group. And all other matrices, since you have only zeros in the diagonal, all other group elements, the character is going to be 0. So this is going to be important in a minute. Okay. So let me first show you this result. I'm going to show you that the regular representation is indeed a representation of the group. Okay. To show that, I essentially need to show that the multiplication table is satisfied. That is, if I have a matrix corresponding to the product of BC in the regular representation, this is equal to the products of matrices in the regular representations of B times the matrix corresponding to C. So if I show this for all arbitrary B and C, I show that the set of matrices will satisfy the same multiplication table as the group, so this will be a representation of the group. Okay. Okay. To show you this, first let me write the matrix elements of the regular representation in general. I can write the matrix elements of a regular representation corresponding to any given group element X. I will index this in the following and convenient way. The row is always the inverse of some group element, and the column is another group element, AI. Okay. And by definition, this is going to be equal to 1 if this product is equal to X. This is basically the definition of the regular representation. And then it's going to be 0 otherwise. Okay. So I basically wrote in a mathematical form the procedure to construct the regular matrix that I used in the previous slide. Okay. So you have 1 in the matrix whenever the product of row and column is equal to the same element of the matrix I'm considering. Okay. Okay. So let me just use this notation. I will use this notation to calculate this product of matrices. So we can calculate the product of matrices in the usual way by summing of over the inner indices, right? So you have the matrix corresponding to the product, and then I'm going to focus here on the particular matrix element AK inverse AI. Then this is equal to a sum over inner indices AJ, and then the matrix corresponding to the element B AK minus 1 AJ, and then the matrix corresponding to the element C, AJ minus 1 AI. So what we see here is simply the usual expression for the product of two matrices. In this case, two square matrices. You see that the inner indices are the same, and I sum over those. Okay. All right. So now, if I apply this result here to these two matrix elements here, I can basically see that this is going to be 0 unless AK minus 1 AJ is equal to B. And this is going to be 0 unless AJ minus 1 AI is equal to C. Okay, I can apply this result, this explicit definition of the matrix elements. I can just put this here into the summation, and I will then arrive in the following result. So this is going to be 0 unless these two conditions apply simultaneously. And then when they apply simultaneously, this is going to be equal to BC. This is going to be equal to BC. Okay. Unless, so what's going to be equal to BC? AK minus 1 AJ, which is the first member of this first factor of this product, and AJ minus 1 AI. You can see this cancels with that. This is equal to AK minus 1, sorry, AI. This is AI. So this is AK minus 1 AI. So then I arrive in this result, and this is basically the definition of the regular matrix element of BC. Okay. Again, I apply the same definition here now to BC, and I get this result. So I have basically I have shown that if I use these definitions to the elements of this regular matrix, when I calculate this for BC, I arrive in a consistent definition for BC. So, and this is a proof that this relation is valid. Okay. So the regular representation is a representation of the group. Of course, it's a reducible representation of the group. And now, what I'm going to show is that the regular representation. I'm going to show you this theorem. I'm going to show you that the regular representation contains each irreducible representation a number of times equals to the dimensionality of the representation. Again, this is a very important result because actually it allows us to find all the different irreducible representations of the group. Okay. If I know how to construct the regular representation, and if I show this theorem, then I know that the regular representation, if I put it in a block form, it will contain each representation of the group a certain number of times. So if I do this procedure, this allows us to find all the different irreducible representations of the group. It's not the best way to find the different irreducible representations of the group, but it is a straightforward way to find it. So it's not very much used. There are easier ways to find irreducible representations of the group, but I mean, this is a straightforward way. It will always work, okay? So what does that mean? What does this theorem mean? It means that, for instance, if you use again the group P3 as an example, it says that this regular representation contains gamma 1 just once, because gamma 1 is a one-dimensional representation, gamma 1 prime once, because again it's a one-dimensional representation, and it contains gamma 2 twice. Okay? So the regular representation of P3 has dimensionality 6. We have seen that already by explicitly construction of the regular representation. Okay. All right. So let us show this result. Let me prove this theorem. So since the regular representation is a reducible representation, as we have seen already, I can always write the character of regular representation corresponding to the class CK as a linear combination of the characters for all irreducible representations gamma I with coefficients AI, and these are the characters of the different irreducible representations of the group. Okay, so we have already shown you that AI is unique, and we have explicitly calculated AI as 1 over H, sum over all classes, number of elements in each class, and K, and this is chi gamma I CK complex conjugated, and then the character of the regular representation for the same class CK. Okay? All right. Now we're going to use this result that the character for the regular representation is it's zero for all classes, for all group elements except the identity, right? That it's in a class by itself. So this is 0 unless we are talking about the identity class. So this summation of classes, actually only one of the different terms is non-zero, and that corresponds to the identity. Okay? So then I can write AI simply as 1 over H, and E, the number of elements in the identity class, is just 1. So the number of elements in the identity class is always 1. The class, the identity is in a class by itself. And so this is equal to H, right? This is the trace of the regular representation. So this is there's an H here. And this is the trace of the identity representation associated to the irreducible, is the trace of the identity class, the identity element, associated to the irreducible representation gamma I. So this is simply Li, the dimensionality. Oops. Sorry. This is the dimensionality of representation. Of representation gamma I, okay? This is Li. Then I have this result, AI equals to Li. Li being the dimensionality of the representation gamma I, okay? Alright. So, and this is what we wanted to prove. We wanted to basically prove that the number of times AI that a given representation is contained in the regular representation is equal to the dimensionality of the representation Li. Alright? Okay. This completes the proof. Okay. The final result for this lecture, that it's again very important, is this one. So that also is I could say that the most important result coming from the concept of regular representation is this one. This relates the order of the group to the dimensionality of the different irreducible representations of the group. So if you sum over all irreducible representations of the group, the dimensionality square, then the result is equal to H. Again, this is an unsuspected result, and it's then a very beautiful result and important. We have shown this result in the last lecture, this inequality, but now we're going to show that it is the equality that holds. Okay. All right. So the proof is very simple, and again, I'm going to use the fact that the character corresponding the character of the regular representation corresponding to the symmetry operation E, the identity, is equal to H, is equal to the order of the group. Okay. So, and I'm also going to use this result again, this decomposition result again. So this is equal to sum over all irreducible representations gamma j, the coefficients aj, and then the characters corresponding to the same symmetry operation identity, but now the characters of the representation gamma j. Okay, and so this we have in the previous slide. You have shown you this is Lj, and this is also Lj, right? This is the trace. This is the trace of the identity matrices with Lj rows and columns. Okay, so this is basically sum over gamma j of Lj squared, and this completes the proof. So H is equal to the sum. H is equal to the sum of all dimensions squared of all irreducible representations. So we're going to see in the next lecture that all these results that we have obtained here, the orthogonality theorems for character, and also these results, we're going to use them in a very practical manner to set up character tables, to obtain the character tables for different groups. Okay. But before we finish this lecture, let me just show an example of this relation again for the group P3. Let me just show that it holds for group P3. So this is the character table. This is the character table for the group P3. We have seen that many times already. And we know that the order of the group is H is equal to 6 in this case. So the order of the group H is equal to 6 for the P3 group. So it must be equal to the sum of the dimensionalities of the representations. You have two one-dimensional representations, gamma 1 and gamma 1 prime, and one two-dimensional representation, gamma 2. So basically the last result of we have shown you this lecture means that 1 square plus 1 square plus 2 square equals to 6, which is of course it's true. So this is the last result of this lecture, and there's a verification of this particular theorem to the specific example we have discussed, the P3 group. So in the next lecture on Wednesday, as I said, we're going to apply all these results to set up, to learn how to set up, to construct character tables of the different groups, and then we're gonna look at different character tables for various point groups, and try to understand also a little bit of the different notations that people use for point groups in group theory. Okay.